Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are looking at a last section of aldehydes and ketones. Specifically, we are going to look at molecules which possess both the alkene and carbonyl functional groups, the alpha-beta-unsaturated aldehyde and ketone. Now, if I localize the ketone or aldehyde group, such as this position, I can identify the proximity of the alkene with regards to a carbonyl group as being on the alpha carbon and a beta carbon. This carbon's also alpha. And hence the term alpha-beta unsaturated. Unsaturated meaning an olefinic or alkene-like bond. Alpha-beta unsaturated, in this case a ketone. Now the two pi systems, unlike a diene, although they're conjugated, they are polarized. That is, the pi system being attached to an electronegative oxygen represents a polarized pi system. This can be drawn very nicely and indicated by resonance structures. I can, for example, move the pi electrons out towards the oxygen and produce a minor resonance contributor. Which produces an electron deficient carbon. Negative charge on oxygen, positive charge on carbon. Carbon has only 6 electrons, so it's a minor contributor. I can also draw a resonance contributor where I shift these pi electrons, thusly, and I get a CH2, CH, now a double bond, C, O minus. And the positive shifts out towards the CH2. Now the effect of doing this is to produce a resonance hybrid. This resonance hybrid that can be formed from the 3 resonance contributors would look something like this. Remember, resonance structures are drawn because valence bond theory requires bonds to be localized between 2 atoms. It gets around this requirement by creating resonance structures. None of the resonance structures exist. What exists is the resonance hybrid. In this case, the resonance hybrid would appear something like this, in which there is a delocalized pi system out over the oxygen, and you have a delta plus off the terminal CH2 and a delta plus off the carbonyl. And a minus or delta minus on the oxygen. Okay, now, because of this, the 2 carbons would be susceptible to attack, if you like, by nucleophiles. However, this attack could be facilitated by initial reaction with an electrophile such as an acid. We could increase the nucleophilicity of these positions if we favored the formation or removal of the negative charge out to the oxygen. This can be done by reaction with acid, and hence it's referred to as electrophilic 1,4 addition. So let's start by looking at electrophilic. (1,4) addition. If we start with CH2, double bond, CH, C double bond O, CH3, And I hit this with HCl. React this with HCl, I get Cl, CH2, CH2, C double bond O, CH3. Now the mechanism proceeds through an initial electrophilic attack of the oxygen by a proton. HCl is a reasonable acid. And if we look at the mechanism, step 1 could be drawn as simple protonation. So I could start with the CH2, double bond, CH, C double bond O, CH3, attack with H plus. This certainly would be an equilibrium and reversible. And of course, if we examine this, the presence of the acid increases, if you like, the formation of the enol, or the preponderance of the resonance contributors, by increasing the electronegativity of the oxygen by making it positive. More electrons are withdrawn, and the delta plus at the 2 carbon positions increases. Now those are the delta pluses that would be located here and here. We often represent this by drawing resonance structures. So I can draw the first resonance structure, if you like. Plus here. Now, if you like, resonance structures don't exist, but if you like, the percentage contribution made by this structure to the total resonance hybrid would be greater in this case because of the protonation. Effectively, if you like, the protonation increased the electronegativity of oxygen, which produces large delta plus. This was formed by these pi electrons moving out on the oxygen. Now likewise, we could move the pi electrons of the alkene between the CH and C of the carbonyl. If we do that, we would get something like this. An enol. And of course, you still have the CH2, except the positives now on the CH2. So the first step is electrophilic attack of an acid to produce a resonance stabilized, alpha-beta-unsaturated carbonyl system. And if a nucleophile now attacks, step 2, nucleophilic attack, a nucleophile would be attracted to both positive charges. All right, so let's take a look at that by examining this resonance contributor first. So if I redraw that contributor, I have a positive here. In the case of HCl, the nucleophile is Cl minus. If Cl minus attacks, you get ClCH2. CH, double bond, COH. The problem, of course, with this as product is that this is an enol. And as we learned, the enol form is typically less stable than the keto form. And the enol form will tautomerize. Okay? So it will undergo what we call tautomerization. Tautomerization is where you shift one or more hydrogens and a pi bond. So it's not resonance because you're moving atoms as well as electrons. And if you do that, you could envisage dumping in some electrons, creating a negative, losing proton here, positive adding in this position, and you will get Cl, CH2, CH2, C double bond O, CH3. Now, it looks like you added HCl across the pi bond that was originally in this position. However, the 1,4 addition does lead to the enol. Originally in the initial enol form, if this was position 1, 2, 3, 4, then the chlorine added to position 4. Okay. All right. Now, compare this to what occurs when we actually react with a diene. What if we had a reaction with 1,4-butadiene? Well, if I draw the butadiene in an analogous position to the methyl ketone, it is possible to do 1,4 addition of HCl and produce Cl, CH2, CH2. Oops, that should be a CH. Double bond. C. CH3. CH3. Where H added to this position, H added here, and in so doing so, you got the carbocation and you added the Cl to this position. Very reminiscent of the enol. The only case in 1,4 addition to the diene is CH3 stable. This is in simple alkene. There's no such thing as tautomerization that takes place. But in the case of the enol, it's unstable. However, remember, for nucleophilic attack, this was just one of the resonance contributors up here. If I drew its other resonance contributor, and put the positive charge on the carbonyl, could not the chloride have attacked this position? Could not Cl minus go for the carbon of the carbonyl and give us 1,2 addition? Well, imagine what would happen if it attacked. You get CH2, excuse me, double bond CH, and then you'd have a COH Cl. Now, earlier in this course, we talked about geminal diols, or OH groups, off of the same carbon, that they were formed of hydrated aldehydes or ketones. And we learned that geminal OHs could easily kick out water and just become a carbonyl. They were less stable. It turns out the chloro, being such a good leaving group, is also, because it's a good leaving group, unfavorable in a geminal configuration with an alcohol group. That is, the chloro can easily be kicked out. So if going down is plus chloride minus, then going back up is minus Cl minus. This product is unstable. And so while attack of this resonance contributor is possible, it does not lead to a stable product. It does not lead to a stable product. Because it's unstable, the chloride immediately gets kicked out, and you get back to the original carbocation. Only attack at the 1,4 position here leads to eventuality of an enol, which can tautomerize to a stable product. And this product is stable. So, if you use acid, okay, if you use acid like HCl, you get electrophilic, (1,4) addition. Okay. Well, what happens if you don't have acid? What if you use a powerful nucleophile instead? What happens then? Well, in the case of nucleophilic attack can lead to both 1,2 or 1,4 addition. Whereas in the case of HCl, the 1,2 product wasn't stable. Nucleophilic attack gives rise to both possibilities, 1,2 and 1,4 addition. And so we want to take a look at that next. And we'll use relatively strong nucleophiles in this case because, remember, we don't have the acid to increase the concentrations or increase the delta plus on the carbonyl carbon and the beta carbon. Now, if we undergo 1,2 attack, 1,2 attack, if you like, 1,2 attack is referred sometimes to carbonyl addition. If we do 1,4 addition, 1,4 is often called conjugate because you're attacking a carbon off a conjugated double bond. Conjugate addition. Let's look at an example of this reaction and consider what actually is taking place. If I take the same alpha-beta-unsaturated ketone that I used last time and I react it with a powerful nucleophile this time, for example, let's use Cn minus. Cn minus, remember, is C triple bond N, and there's 2 lone pairs with a negative charge on carbon. This carbon can act as a nucleophile. If it does, it can add in a conjugate manner, producing the conjugate addition product. We'll get NCCH2, CH2, C double bond O, CH3. And if I was to name this molecule, although we haven't had the nomenclature of CN groups, this would be 4-oxo 1, 2, 3, 4, 5 pentane, and a C triple bond N is referred to as a nitrile group. So pentane nitrile. We could say pentan 1 nitrile, but the nitrile is at carbon 1. It has to be a terminal group. Okay. What is the mechanism for this reaction? How does it proceed? Well, as you can imagine, Cn- being a powerful nucleophile, you have a delta minus an oxygen. You have a delta plus on this carbon and a delta plus on this carbon. To form the conjugate product, the Cn- attacks that delta plus. The pi electrons shift this way. And these pi electrons move out into oxygen. If you do that, you get a CH2 with your Cn attached to it. You get a CH double bond C O minus. You get an enolate anion. Now, of course, enolates are resonance stabilized. We can dump these pi electrons, create a pi bond, and move these pi electrons out to the carbon. If we do that, we have a CH2, Cn. The CH, the pi electrons, became a lone pair on carbon, and we now have C double bond O. So the minus is at carbon now. And that's quite basic. In fact, it's very basic. And so your cyanide would be dissolved in something like water, and the C minus would grab a proton off the water, which would become hydroxide. And you'd end up getting CH2, Cn. The CH grabs the proton, becomes a CH2, leaving your carbonyl, CH3. And so there you have your conjugate addition. Okay. Well, what about attacking this position? Why not attack this carbon? After all, there's also a delta plus there. Will you get a mixture of products? If you attack the carbon I've labeled as red. Will you get carbonyl addition? Well, typically, carbonyl attack, okay, or carbonyl addition of cyanide, okay, and also, in the case of amines, leads to reversible and less favored reactions than conjugate addition. But it can occur in some cases. So, and we're going to look at an example, some examples of where we might get, in the cyanide case, a carbonyl addition product. So let's draw a starting material again. Let's just start and consider at this time attackable sites. And electronegative oxygen produces delta pluses here and here. If we did conjugate addition, we get the product where the cyanide adds here. Remember, this is conjugate, called conjugate addition. If we attack the carbonyl delta plus, Cn would go there. That would put an oxide, O minus out here, which would grab a proton, and you'll end up getting this. And this is carbonyl addition. Now, the first thing that might jump into your head is that, oh, that's like geminal attack with the chloral. You have the OH and the chloral off the same carbon. It was unstable. So putting cyanide in this position would be unstable. Well, let me say, remember, cyanide is a far more powerful nucleophile than chloride. Because of that, the carbonyl attack, it doesn't lead to quite as an unstable product as it does in the chloral case. Now, when there's no steric effects, even with a strong nucleophile cyanide, conjugate addition is favored. But we can drive it to undergo carbonyl attack. How? Well, one way is to increase the steric nature of this carbon. Make this guy more bulky. If we reduce the bulk, that is, let's do some modifications. Take our carbonyl and reduce the bulk on the carbonyl by making an aldehyde, okay? That should make the carbonyl more susceptible to nucleophilic attack. There's less steric hindrance around it. And on the case of the conjugate site, let's put, instead of hydrogens here, let's put a couple ethyl groups, some bulky ethyl groups there. Well, if we make it more bulky, nucleophilic attack due to steric repulsion is less likely in the conjugate position. This is less likely. Whereas this guy's nice and open. And so, in actual fact, in a molecule where there's a lot of steric hindrance here, you most likely get attack here. And the most likely product in this case would be the conjugate addition product. Okay. So you get the OH and the CN here. So with cyanide, you can get, in rare instances, carbonyl addition. But you have to use a lot of steric bulk to do it. What happens, however, if we keep increasing the strength of the nucleophile? Notice chloral would not go here because it was too weak a nucleophile and it was reversible and carbonyl addition wasn't possible. Increase the nucleophilic strength to cyanide, carbonyl addition becomes viable, but conjugate addition is still favored. Except in the case if there's a lot of steric bulk around this carbon and not much around the carbonyl carbon. You can get, on rare occasions, cyanide predominating. Well, what if we go beyond the nucleophilic strength of cyanide? Is there any way we can favor carbonyl addition without any steric hindrance effects? And the answer is yes. You can imagine a scenario where instead of cyanide, okay, we use CN as our reagent. I'm going to replace CN this time, and I'm going to use instead lithium dimethyl cuprate. I'll use that in step 1. And of course, step 2, I'll throw an acid to destroy the copper reagent. Now, remember, dialkyl cuprates are weaker reagents, weaker alkylating reagents than Grignard or alkyl lithium. But they are still extremely powerful reagents. Also, the mechanism is complex and not well understood, and most likely involving free radicals. Right? If we use lithium dimethyl cuprates, we also favor conjugate addition reactions. That is, what are we adding? We're adding a methyl. The methyl actually goes on here. You know, you could envisage it going here for carbonyl addition. And indeed, with lithium dimethyl cuprate, which is a weaker alkylating agent, we get the consistent idea of weaker reagent yielding and supporting conjugate addition. But we know that Grignard reagents and alkyl lithium reagents, such as methyl lithium, are much stronger alkylating reagents. And so what happens if I change this to lithium with a methyl group? Methyl lithium. Well, if I change it to methyl lithium, in that case, the carbonyl product is major, and the conjugate addition product's not formed, or formed in lesser yields. Okay, so methyl cuprates favor conjugate addition, but methyl lithiums favor carbonyl addition. What if we have the powerful nucleophile H-, far more powerful than cyanide? Okay. Well, H- is comparable to methyl- in a source. What if we use lithium aluminum hydride? Well, you recall, we've already covered this reaction. Lithium aluminum hydride attacks polar pi bonds. It will not attack the alkene bond, which is less polar. And so lithium aluminum hydride, if you have a choice, add an H here, or conjugate addition would have added the H here. The reaction that occurs is this one, carbonyl addition. Now, what's really interesting is if I cover this reaction with Grignard reagent, methyl magnesium bromide. Methyl magnesium bromide, again, would either put a CH3 here in conjugate addition, or CH3 in this position for carbonyl addition. Methyl magnesium bromide, yes, it's powerful, and yes, the carbonyl product is favored, but you actually still get a little bit conjugate addition, 20%. There you go. So if you use Grignard, you get a mixture of products. This allows us to make a summary of reactivities or reagents and whether you get conjugate or carbonyl addition. We can summarize it as follows. 1. Metal hydrides such as, remember what they are, lithium aluminum hydride, sodium borohydride, or alkyl lithium, such as methyllithium. What do they give you? They always give you carbonyl addition. Okay? 2. Lithium dialkyl cuprates such as lithium dimethyl cuprate, these always give you conjugate addition. And 3, Grignards are a little more complicated. Grignard reagents, remember we had 70% carbonyl addition. Grignard reagents such as methyl magnesium bromide, favor carbonyl addition. They favor carbonyl addition. But imagine if you could make the real bulky groups around the carbonyl, you could probably shut that down and shift it to conjugate addition. So like cyanide, it would probably be subject to steric effects. Four, because the reactions are reversible, cyanides and remember imine formation was reversible, so attacks by amine, cyanides and amines. Favor conjugate addition. But they are subject to steric effects. So watch for steric effects as well. Okay, so let's try one problem that exemplifies these 4 reactions and see if we can make some predictions about it and apply these 4 rules. Once again, the 4 rules are metal hydrides and alkyl lithium will favor carbonyl attack. Lithium dialkyl cuprates will always do conjugate addition. Grignard reagents will favor carbonyl addition, but they are subject to steric effects, and cyanides and amines will favor conjugate addition. These rules apply for nucleophilic, okay, 1,2 and 1,4 addition to alpha-beta-unsaturated carbonyl compounds. Suppose I had the following molecule. And I asked for the product with lithium aluminum hydride. Well, lithium aluminum hydride is a polar reagent, and we know it does not attack the alkene, so it would be expected to add H- to the carbonyl. The acid would then protonate the oxygen, producing an OH and leaving the alkene intact. Likewise, if I tried it with lithium, methyl lithium, would be expected to attack the carbonyl, and you'd get the OH here, a CH3, your carbonyl attack, and the alkene would remain unaffected. However, if I used lithium dimethyl cuprate, with acid in the second step. And remember, the 1 and 2 here again means add the reagent first, let it react, and then step 2, add the acid. This favors conjugate attack. And so the methyl would go in this position, and the double bond O would be retained. If you used cyanide or Grignard reagent, Grignards would favor the carbonyl attack. They would tend to form major, this guy, but it is controlled by steric effects. The fact that the conjugate position has some steric effect would favor this, so Grignard would be expected in this case to go the same way as methyl lithium. It may not go 100%, but it would be awfully close. So if I use methyl magnesium bromide here, I would get the same thing. What about cyanide? This one's hard to predict. Cyanide prefers conjugate addition, no doubt about that. However, we have the CH2 of the ring and a methyl, which suggests the conjugate position is a bit hindered. We have a ketone, a bit exposed. Is there enough steric effect to drive it towards carbonyl addition? It would probably give you some carbonyl attack. In this case, hard to say, but it would probably be some percentage mixture. Would be very hard to predict which one's going to be major, but it's quite possible that you'd get a little both. And so I would probably draw both. And in this case, it'd be very hard to predict which would be major. So there's both products. Steric effects might suggest that the carbonyl addition might predominate. And, to be honest, I would try to make the reaction more clear cut. On a test, you'd be less likely to see something like this. I would make it very sterically hindered one way or the other. And you could then determine where the groups would go. Okay, so there you have reactivity of alpha-beta-unsaturated aldehydes and ketones. Two reaction mechanisms: electrophilic 1,4 addition with acids such as HCl, and nucleophilic 1,2 and 1,4 additions, which depending on the reagent either give carbonyl addition or conjugate addition. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.